We have a very interesting session on intention and free will, and we're going to revisit some experiments done decades ago by Benjamin Libet. And first we'll have a full plenary session, and then we will have a panel with 6 short talks, and then a discussion with the 6 panelists and our first plenary speaker, who is, I'm very happy to introduce, Aaron Schurger, from the INSERM Cognitive Neuroimaging Group at the Neurospin Research Center, where Stan DeHaan is from as well, in Saclay in France. And he had a recent paper on this in, was it PNAS? In PNAS on this topic that he's going to talk about, which is 50 years without free will. Here you go, Aaron Schurger. Give him a round of applause.
Thank you, and I'd like to thank Stuart and the organizers for a great conference and for inviting me. It's a great honor. Many of the things that you do in a given day are in fact in response to stimuli. For example, the traffic light ahead turns red and you press on the brake pedal, the phone rings and you answer it, someone calls out to you and you reply. But many, if not most, of the things you do in a given day are done autonomously. There is no stimulus telling you what to do. And this is the question that I've been interested in the past few years, is how the brain initiates actions when there's no cue. So take, for a simple example, you're reading the newspaper in the morning and you have your cup of coffee there. You're not particularly thirsty, but at a given moment, you reach out to take your next sip of coffee. Now, that sounds like a very trivial example. Maybe it's even an insult to free will to think that reaching for your cup of coffee is an act of free will. Although I never feel quite as free as after I've had my morning coffee. Consider this. Why did you initiate that reaching movement precisely when you did and not, say, 200 milliseconds earlier or later? So these are the kinds of questions that keep me up at night. So this, what I call the deciding moment between not moving and moving, for shorthand, I call it the neural decision to move, or the neural decision to act. I use the word decision not in the way that we typically use it, like the decision to go to the grocery store after work. It's an abstract use of the word. So, for example, a neuron, when it fires, has made a decision that its inputs are adequate for it to produce an output. When is the neural decision to act relative to the onset of the action itself? And how is it related to the conscious urge to move? These are the questions I want to take up today. So one of the seminal papers, if not the seminal paper that started this area of research, at least in modern times, was published more than 50 years ago in 1965 by Kornhuber and Decker. For those of you who don't read German, there you go. They did something that was quite novel at the time. They didn't use any stimulus cues. They let their subjects produce a movement, I think it was just flexion of the wrist, when they wanted to, at sort of odd intervals. And while their subjects were doing this, they recorded EEG. And they discovered what I think many of you are familiar with, the cortical readiness potential. So it's a slow buildup of scalp electrical potential, beginning up to 1 second or even more before the onset of the movement. I don't know if you can see a pointer on the screen. Yes? Okay, yeah. So this is recorded over the motor areas of cortex with EEG, and here, contralateral to the hand that was doing the moving or the foot that was doing the moving, you see this slow buildup. Notice, by the way, that negative is up, and these sometimes it's down and sometimes it's up. Just be sure to watch the labels. So, in spite of years of controversy about precisely what this means, the basic notion that it represents the electrophysiological sign of planning, preparation, initiation of volitional acts. That basic definition has held, or interpretation of the readiness potential has held. And in the interim, the same phenomenon has been observed in single units in premotor cortex of human epilepsy patients, down here by Fried et al. In 2011. And it's also been found in primates, rodents, and even my favorite in crayfish, who have no motor cortex. In fact, they have no cortex at all. About 20 years later, Benjamin Libet, who knew about the readiness potential, was interested in the feeling, or the feeling of having decided to initiate an action, or what he called the urge. He was interested in where in time this urge would be found relative to the time course of the readiness potential. So he recorded EEG while his subjects monitored a clock dial. I suspect this experiment is very familiar to many of you. Subjects monitored this rapidly rotating clock dial, which did 1 revolution every 3 seconds, and were told at odd times to make an abrupt movement spontaneously without any pre-planning. So it says down here, be spontaneous, which is a strange instruction. But oddly enough, subjects are able to do this. They do find it strange at first, but they do it. And I'll come back to that later. So he recovered, of course, the readiness potential. It's very robust, and it appears very reliably when you ask subjects to make movements at their own pace or at a time of their own choosing. What he found that was remarkable and made history was that if you consider the readiness potential to have began somewhere back here, if you can see that pointer, the average time at which subjects reported being conscious of their urge to move was some 300 or more milliseconds later, about 200 milliseconds before the actual initiation of the movement. So this was interpreted to mean in simple terms that we can't possibly have conscious will over our actions. The brain has already decided to produce that movement well before we're even conscious of our own urge or our own intention to produce the movement. So this has given rise to the prevailing view, which I think is still more or less the prevailing view, that what happens back here in time, at about the time that the readiness potential, quote unquote, begins, is some sort of a decision, and all the rest is outcome. And at some point, far down the line, there's the point in time when the self becomes conscious of the decision to move. I would like to offer a new perspective on the interpretation or meaning of the readiness potential by way of a thought experiment. And this is a thought experiment. I didn't do this experiment, but I did actually run the simulations. So imagine that it's flu season and you're doing a study on the etiology of the flu. So you take a large population of people at the beginning of the season and you fit them with one of these wristbands that keeps constant track of their vital signs. Let's say it keeps track of their health points, like in a video game. Okay? So if they get exercise and eat good, then on those days their health points might be a bit higher. If they party too much, drink too much, and get up early, their health points might be lower, and so on. So this is monitoring their health points minute by minute throughout the flu season, and if they should come down with the symptoms of the flu, they're to press a little button, which marks the time of onset of the flu symptoms. And so what we want to do in our study, similar to what we do with the readiness potential, is to take the data epochs from the ones who came down with the flu and align them to the moment at which the flu onset, and examine what happened in advance, just before then. So here are just some sample traces from some of the participants who actually came down with the flu. A couple of things worthy of note. One is that we don't have anybody here who didn't come down with the flu. Although there were plenty who didn't, we're not going to study those, right? Because we have nothing to time lock to. Second, notice that their health points are not flat. They wander, they meander around. They're noisy, right? They're not perfectly stable. Of course, at the moment that they come in contact with the virus and come down with the flu, their health points drop precipitously, stay low for a while until they start to get better again. So now let's say that we do, just like we do with the readiness potentials, we find these events, event being onset of the flu, and we align the data to those events and take an average and look and see what happened in advance. So here's the road to the flu. And we see this slow decrease in health preceding the onset of the flu symptoms. This makes sense, that as you're getting the flu, you might get a little bit more and more under the weather gradually. and then really plummet at the end. Now this is a thought experiment, so we know everything. So here's something that we also know, which is that this is the time that they came in contact with the virus. So now, looking at this, something seems really wrong, right? Because if the virus is, contacted with the virus is what gives you the flu, how can you already be getting sicker in advance? Now, one possibility is that the immune system is prescient. It knows that you're going to come down with the flu in a few days and says, well, I might as well get the ball rolling now, right? But we know that something seems a little fishy with that explanation. And the key is to notice that you don't get sick just from getting in contact with the virus. You catch the flu from coming in contact with the virus when your immune system at that moment happens to be ill-prepared to fight it off. So here's one example. A participant who came in contact with the virus many, many times, but only actually contracted the flu when their health score was already on its way down, just randomly, just happened to be on its way down, and that's when they caught the flu. And so, of course, if you time lock to these events, you catch that incidental decline in health that tends to precede getting the flu. It doesn't mean that you were planning or intending to get the flu. So this happens because intrinsic fluctuations in the relevant variable, in this case your health points, get caught in the flash photo of event-locked averaging. And I'm asserting that that's the same thing that happens with the readiness potential, that that's where the readiness potential comes from. Now, are there spontaneous fluctuations in neural activity that could account for this? Absolutely. Neural activity fluctuates constantly, and it looks like this. It looks like this kind of noise here on the top. This is autocorrelated noise, or sometimes called pink or brown noise. It does not look like this. This is white noise. If it looks like this, something's wrong with your equipment, or something's very wrong with your subject. So what makes this noise, quote unquote, autocorrelated is that most of the energy is in the low frequencies, and there's ever less and less energy at higher and higher frequencies. White noise has equal power in all frequencies. So this is the kind of noise we have in the brain. In fact, this is the kind of noise that you have in just about any system in nature, including the weather, and at all spatial scales. So from probability of synaptic vesicle release all the way up to the residuals around your reaction times in a behavioral task. So what got me started with this research was a simple question. How might a machine comply with Libet's instructions? Supposing I was to build a robotic arm that did Libet's task. One easy way to do it would be to take advantage of noise that's inherent in that system. So no matter how much money I spend on my components, I will have some noise at some level in my robotic arm. And so what I can do is I can push up the actuator closer to the threshold and then just wait. And eventually it will cross the threshold by accident because of the noise, and the arm will make a little movement. So this is ultra simple, but it gets the job done. So that's what I started with. And so together with my colleagues, Stan Dehaan and Hako Sit, we came up with these two premises. One is that the brain uses the same mechanism for decision-making in a task like Libet's as it would in any decision-making task. That's accumulation of evidence, of neural evidence, up to a threshold. Except in this case, there's no evidence per se. There's mostly internal noise, plus a weak imperative to move. Now, what's this weak imperative to move? You tell your subjects, and I tell my subjects when they come in to do Libet's task, you can make the movement, lifting up your finger, as it happened to be, whenever you want. There are no rules. I'm very explicit about that. And yet, no subject ever waits longer than about 30 seconds to produce a movement. They could, if they wanted to, wait all day. They could never move, and they'd still be complying with the instructions. But because they're in the lab to do an experiment about lifting your finger, somewhere underneath all of that implicit is, move your damn finger sooner or later, right? So that's this weak imperative to move. It's fine. It doesn't kind of ruin the experiment. It just means that it puts some constraints, right? Within a time window of 10 seconds or so, they're roughly free to move their finger whenever they want. And they do. Second premise, when the imperative to produce a movement is weak or absent, the precise moment at which the decision threshold is crossed is largely determined by spontaneous subthreshold fluctuations in neural activity. So here you have this red line represents this weak imperative. It's weak relative to the noise. And you can see that had the noise behaved a little differently, it might have crossed the threshold here. And if the noise had behaved differently here, it might have crossed the threshold, well, off the page, right? So the noise can play a role in crossing the threshold, and since we time lock to supposedly the time of the threshold crossing, then we recover the autocorrelation function of the noise. So this is the model that we used, and compared to some of the math that people have been throwing around in the last couple of days, this is kid stuff. So this is just a simple differential equation. It's called a leaky stochastic accumulator. It has 3 free parameters. It has this drift parameter, which is like this imperative, this weak imperative to move. It has leak, which makes the whole thing more biologically plausible, and a threshold on X. And so this is what, if I run a dozen or so runs of the simulation, this is what the traces look like. They're all superimposed on each other. But basically, it tends to move up a little bit closer to threshold, and then reaches stationarity about here, and then just wanders randomly around that point until at some point it happens to cross the threshold. And when it does, I mark the threshold crossing time. And we can look at the distribution of these threshold crossing times. These are analogous to how long the subject decides to wait before making his or her movement. And you can also look at the average trajectory of this decision variable up to the threshold as a surrogate for the readiness potential. And when you do that, when you time lock to these threshold crossings and average together the trajectories, you get something here on the right that looks suspiciously like the readiness potential. So what we did was we fit the distribution of the threshold crossing times to the empirically observed distribution of waiting times and got a really, really nice fit. And then with those very same parameters, we asked, well, how well does the average trajectory fit the readiness potential? And as you can see here, it fit extraordinarily well, up to about 150 milliseconds before the onset of movement. So we wanted to find another way to test our model more formally. And so we thought of the following prediction and experiment to do, which we call the Libitus interruptus experiment. I don't know where that name came from. It just popped into my mind. We were doing the experiment, and that I needed to give the folder a name on my computer where I was keeping the data. So after doing the classic Libet task for about 20 minutes, you repeat the same task again, except every so often there's an occasional click, a quiet little click, and you're told if you hear the click, press the button immediately. Don't wait, as quickly as you can. Otherwise, just keep doing the task as you were. Wait as long as you feel like waiting, and then make a spontaneous movement. So if the click is heard before the movement is made, then the subject has to press the button immediately. That's the bottom line. So consider this simple model of what's happening in such a task. You have a threshold. You have spontaneous fluctuations underneath the threshold. Now, if the interruption happens to arrive here, then the reaction time to that interruption, to that click, will be given by this fast rise, this fast climb up to the threshold. And depending on how far the signal is from the threshold at the time that the interruption happens, your reaction time will be longer or shorter. So if you're interrupted here, your reaction time will be like this. If you happen to be interrupted here, where the signal is already quite close to the threshold, then your reaction time will be that much shorter. And of course, if you made a spontaneous movement, then any interruption after that will never happen. So the prediction is that fast reaction times to interruptions should be preceded by a buildup in negative signal amplitude beginning well before the interruption itself, even when the subject was not preparing to move at that particular moment. And that is indeed what we found to be the case. So I unpack this slide a bit. On the left here, we have the data time locked to the movement, and this is the actual empirical data, and down on the bottom is the model. And on the right, we have the same data time locked to the click. So if you want, you can just focus on the rightmost column, and you can see that there is this slow buildup of electrical potential, nearly linear, for the fast responses to the interrupting click, but not the slow. So this essentially confirmed our predictions. There are a couple of controls that we did. For example, you might say, oh, well, maybe the fast ones were fast just because you happened to interrupt the person at the time that they were getting ready to move. Well, we thought of that in advance, and we told subjects, if you're interrupted and you just happen to be getting ready to move at that moment, say the word coincidence. And so this happened reliably, although rarely, but there were at least a few for each subject, and then we noted those and excluded them from the analyses. So there's some other controls that we did as well, and if you care to, you can ask about them. So our not so prevailing view of the readiness potential is that all of this back here, from about 150 milliseconds before the movement and back as far as you care to go, it's noise. It's spontaneous fluctuations caught in the flash photo of time-locked averaging. And this bit here is a threshold crossing. It's a commitment on the part of the motor system to produce a movement. Before that, no commitment has yet been made. Right? So this is a kind of cute way of summarizing our hypothesis and why it is what it is. So this is sort of a nod to Lamarck, for those of you who know this debate. So Lamarck saw giraffes. He was interested in evolution, and he said, well, giraffes, the neck gets longer because each generation is stretching and stretching and stretching, and that effort to reach higher and higher leaves somehow gets passed on to the next generation, and the necks get longer. I describe this as sort of a kind of cognitive illusion in the sense of Danny Kahneman. So when you see this readiness potential thing building and building and building, you intuitively get the sense of somebody trying to do something. But of course, as hopefully I've convinced you, that need not be the case. So there's been some recent support for what we call the stochastic decision model in a study on rats by Murakami et al., the lab of Zach Manin. So very, very briefly, the rat waits in a little waiting station. His nose is in this little poke hole, and he hears a tone. The tone means to wait for a second tone. And when the second tone arrives, that means that the rat can now leave the waiting station and go to a reward port and get a large reward. But the intervals in between the first and the second tone were variable, and sometimes they could get quite long. And the rat was allowed, if he wanted to just leave the waiting station and go to the reward port, even before the second tone had happened. But then he would only get a small reward. So sometimes the rat got impatient and just went for the small reward, and they focused on those trials, those impatient trials. And what they found, amazingly, was they were recording from neurons in M2 in the rat, which is roughly analogous to premotor cortex. They found neurons whose activity ramped up to a certain threshold, such that when it reached that threshold, the rat initiated his withdrawal from the waiting station and went to get his smaller reward because he had been impatient. Interspersed with those neurons, they found another population of neurons that had a steady tonic, noisy firing rate that covaried with how long the rat waited before leaving the waiting port. So what it looks like they've identified are a set of neurons that are the inputs to, and another set that are the outputs of an accumulator that's being used in a situation where there's no cue. So what they say, and I'll quote them, bounded integration models identify the initial intention to act as the moment of threshold crossing, while explaining how antecedent subthreshold neural activity can influence an action without implying a decision. So in summary, the stochastic decision model accounts for the electrophysiological and behavioral variables in Libet's task. And if I had the time to talk about it, I'd also tell you about some evidence that it can account for the subjective variables as well. It argues for a late commitment in spontaneous self-initiated actions of about 150 milliseconds before the onset of the movement. It argues that conscious intention has a meaningful and reasonably accurate relationship with the decision to move. What I didn't mention, but was implicit in what I said, Libet's subjects on average pointed to about 200 milliseconds before the onset of the movement as the time when they made their decision. In fact, Libet's mistake might have been to just not take them at their word. Maybe their brain was trying to tell them something relatively meaningful, that this was a point in time when something interesting happened, that your brain made a commitment to produce a movement. And finally, it suggests that a pre-event buildup may be a general phenomenon rather than a specific mechanism. So this is something that you might expect to find in economic data or weather and climate data. So back to this point about a late commitment to move. If the commitment to move is late, how can we test that? How can we test to see whether or not the commitment to move builds up from far in advance before the movement or happens very near in time to the onset of the movement itself? This was a study I took up in collaboration with Rob Shapire and Mehmet Bazbug at Princeton University. We tried to map the time course of neural activity predictive of impending movement using a machine learning technique called AdaBoost. So what we needed first, though, was some data that had the proper control condition. So I'll get to that in a minute, and I'll explain how the experiment worked. Subjects just watched a slideshow with pretty slides, and they advanced the slide at their own pace. Whenever they had had enough of that particular slide, they pressed a button. Just before each slide, there was a cue that said either auto or manual, automatic or manual. If you saw a manual cue, it meant that for this next slide, it was up to you to lift your finger to advance to the next slide. And if the cue said automatic, or auto for short, it meant that you just kept your hands palms down on the table and just waited, and the slide would advance by itself. Now, importantly, the viewing time for these automatic trials was drawn from the subject's own viewing time distribution on these manual trials, so that by the end of the experiment, we had two sets of data, one terminating with a movement and one terminating without a movement. And we could time lock then with these two data sets. We could time lock to the slide transition, controlling reasonably well for things like anticipation and how much time had elapsed. So we did this, and then we asked AdaBoost to try and distinguish automatic from manual trials at each point in time in a sliding window. So this, just to give you an idea of what it looks like from one subject, here in white is the sliding window, which will begin to slide soon. And here is an ROC curve. For those of you not familiar with this is a measure of how well the classifier is distinguishing the two kinds of trial. And when this is pushed up in the upper left-hand quarter, that means you're doing well. So when it's right along the diagonal, it means you are not doing much better than guessing. So here this is. And the question is, does our ability to tell these two apart, to predict whether this was a movement or a non-movement epoch, does its time course look like the shape of the readiness potential, or does it look like something much more abrupt? And if I play this for you again, I think you'll see that it is quite a bit like the latter. So if I stop it right here, you see that it's already, in blue, captured a good portion of the readiness potential, and yet has no real predictive power to speak of. And it's not until really at the very end that this takes off. So this is what it looks like when you average them together. We did this experiment just on 3 subjects, but who came in for repeated sessions so that we had lots and lots of data per subject. What's remarkable about this is that the slow, gradual buildup of the readiness potential, which here it is from the very same data, this is the readiness potential from the same data, is noticeably absent from our ability to tell movement from non-movement trials apart. So what are some of the implications then of this late decision account that I've described? Well, one is that the body may play a role in the decision to initiate movement. Now, typically, we think of the decision to initiate movement as something that happens in the brain, and then it's transmitted to the body. My brain decides, move your right arm, and it sends the signal to my right arm, and I move it. But the late decision account allows for another more interesting possibility, which is that the decision to move is an agreement between the brain and the body, an agreement that's made in a sort of dynamical system sort of way, owing to fast feedback from muscle spindles. Because it is a closed loop, and the feedback from muscle spindles is quite fast. Our model also exposes an important limitation of using movement-locked data epochs in the study of self-initiated movement, which is the main approach that's been used to date. The problem with movement-locked analyses is that they discount the prior probability of whatever you find in the average. So consider trying to learn to predict the onset of rainfall based on only a sample of rainy days. It will be difficult to generalize to an arbitrary set of conditions because very often it does not rain. In fact, right here. Likewise, in the study of self-initiated movement, sampling the conditions that are active when a movement is not about to happen is integral to being able to reliably predict when a movement is going to happen. So some of what we're working on now, and these are no longer really future directions because we've already started, in a way, working on this, is to go from trying to predict what people will do in the future, which is something that's fraught with difficulties and is problematic, to trying to forecast behavior based on brain activity using principles borrowed from meteorology research. So this is the readiness potential seen from a different point of view. So where the readiness potential tells you the probability of the signal at each point in time, given a movement at time 0, this distribution here tells you the probability of movement at times t plus tau in the future, given the state of the system now. And this is just a univariate example of this kind of distribution. It takes a large amount of data to build it up, but we are working with collecting a large amount of data from a smaller number of subjects in the research that we're doing presently. What's important about this is that you can distinguish different kinds of processes. So a deterministic process has its own fingerprint, so to speak, when looking at this kind of distribution. And it's something that you can look at across different species and across different spatial scales, and of course can look at in the multivariate space as well. Here I'm just showing you a univariate version. So I'd like to close just with a simple statement. A single human brain is arguably more complex than the entirety of the Earth's atmosphere. And even the local weather can be challenging to predict, except maybe in Tucson. Yet some have begun to conclude that when it comes to the brain, the game is essentially won. We just put brain data together with machine learning, and we're able to predict behavior. I would submit to you that the game has barely just begun. The self-initiation of action remains a profound mystery. And for those who prefer to believe in free will, in my opinion, there is as yet no hard empirical evidence to stand in your way. Thank you.
Aaron, we'll take a few questions for Aaron. In the meantime, can I ask the panelists to come up and can we get one more chair over here, Matt? When you can wait a second.
What's his name?
So thank you so much for an excellent presentation. So I'm wondering if you can you say something from a subjective point of view in terms of the global workspace theory about what's going on for the subject who's sitting there, waiting moment to moment for the sense of deciding to press the button. Mm-hmm. Because in each millisecond, there's some set of processes that are currently occupying the global workspace, right? As the person sitting there, aware of sitting at the table, looking at the computer, and then there comes that moment when the feeling of deciding to act now has entered the global workspace. So can you just say a little bit more about what you think is going on dynamically between the processes that are happening out of awareness around deciding or not deciding to move, and then when that comes into the global workspace and the subject is conscious of it?
So that's tricky, because the main reason that it's tricky is because this is a post hoc report. When the subject reports where was the dot on the circle, right, when you felt the urge to move. He's doing that 1 or 2 seconds after the fact. So we can't really say that that any conscious event necessarily happened at that time. All we know is that the subject perceived it to have happened at that time when probed about it 2 seconds later. So what happens vis-a-vis the global workspace is sort of difficult to reason about, given that. It could be that something is entering the global workspace at the time that the subject is giving their report, or in the final 500 milliseconds before they do that. That may not answer your question, but...
Okay, well, if it's hard to answer, at least that answers the question.
Yes, yeah, it's hard to answer.
Yeah. I'd like to thank you for a brilliant lecture. Thank you. I'm over here to your left.
Yes, okay.
Very simple question. Have you studied criticality in the brain at that time? I've developed a model of free will which depends on criticality states which are at the edge of chaos. It all depends on complexity biology applied to the cortex, for which there's a huge amount of evidence. So if you have criticality states, it gives you automatic freedom to choose. And I showed this in a lecture last night. Would you have any idea about criticality states in the brains of the people you're testing?
I'm not sure I have specific idea, but I will say that I completely agree with you. So I think of this as a complex, I think of the brain and the brain and the body as a complex dynamical system. And the brain, I'm persuaded that the brain is at least during waking, operating at a point of criticality. And that, for example, things like the butterfly effect are real in the brain. We have actually very good there's very good evidence for this about, for example, what a single spike from a single neuron can do. The difference of a single spike in a single neuron.
Brilliant. Thank you very, very much.
Well, thank you. I think Benjamin Libet, he did the most excellent work in neurophysiology. However, his work was not conclusive because he said that the latent period, which is 0.5 milliseconds, which is equivalent to readiness potential, is due to central action or work in the brain for the neurons, either to facilitate or to process the thought for the coming action. So he has a lot of many critics. I review these papers, many critics from Europe and from America here, that the brain does not, the thought is not arising from the brain and could not be arising from the brain. Must be from somewhere else to facilitate a feedback mechanisms. So when I come and work and consider the work of the heart, the intentional conscious act, the heart processes the thoughts, the heart receives information, differentiation, integration, computed this and signal as a conscious act. The time which is equivalent to readiness potential is the time needed for the heart to do this work. And this is my hypothesis.
Okay. Okay. Yeah, I simply don't know what to say.
You said about the finger, so she's just saying it's the
Okay, the heart, not the finger. Well, in principle, I agree with that.
Let's have one more over there, and then you can go first at the general discussion, okay?
I'm on this side.
Okay.
Thank you, thank you, thank you. This is the best presentation on Libet that I've ever heard, so thank you. But I have one major question and problem. Your PNAS paper was in 2012. How come this is the first time I've heard of your paper? And no, I'm serious. I would like to have this community figure out a way to publicize important findings on the understanding of consciousness. And I don't know how one does it, but why did that not?
I can bear some of the blame for that. Marketing was never my forte. I'm getting better at it. I try. I know it's important. If you have something important and worthwhile to say, I think it's worthwhile to try and market it. The other was my choice of the title for the paper. It's, yeah, an accumulator model for spontaneous neural activity prior to self-initiated movement. It gets to the point, but it gets to the point, but that's about all it does. So if you want to help spread the word, please do.
All right, let's thank Aaron. He'll be back for the panel. You probably sit down there. Yeah, please. We'll have more questions later. So now we're going to have a panel. Like I said, we're going to have a discussion at the end. You can go first. So because you've been shut off.
But I had the question to.
Pardon me?
I don't have the question to the panel.
Aaron will be back. You can ask him. He'll be here for the general discussion. So we're going to have this panel now. Everybody's going to have 10 minutes. Thank you. And the first speaker is Ruth Kastner, physicist from the University of Maryland and the University of Albany, who will speak on free will, quantum theory, and the mind-brain.
Let's see if I can do better with or without my glasses. We'll try. Okay. Well, thank you so much. It's a pleasure to be here, and thanks to Dr. Hammeroff for inviting me. I'm a philosopher of physics, and I'm going to be dealing with. I'm going to back up a little bit and deal with some of the claims that I'm trying not to step on the cords here. Okay, sorry. I'm trying to deal with some of the claims in the philosophical literature that have really been overstated, certain arguments that are taken as ruling out free will based on the general character of physical law. And I'm just going to I have way too many slides here, so I'm going to be kind of rushing through, and I hope if, you can ask questions if you're not clear about something. Is everybody okay with the sound level? Okay. Okay, so just very quick, I'm sure all of you already know this, but we're going to just zoom over what do we really mean by free will. This is what I'm going to talk about. There's compatibilism, one theory about free will. Incompatibilism, which has these two features. You can either say we don't have free will, or yes, we do, and as Dr. Schurger so eloquently showed, the Libet experiments really were not inconclusive at all. So then after that section, we're going to look into some of the arguments that have been made about free will supposedly being incompatible even with indeterministic laws like the quantum probability rule. And I'm going to argue that the famous argument by Ted Sider can be refuted. And I'm going to argue, actually, if I have time, that quantum indeterminism could even be seen as requiring volition at some level. And as a side issue, there could be, some people say, well, you need to violate the Born rule to have volition and free will, and they even are making models to that effect, and there's actually some problems in doing that. And then probably won't have time to get to my little toy model of a mind-brain interaction implementing free will. So first, what do we mean by free will? The ability to freely choose one of several options and to implement that choice. And while we may be subject to influences that could favor one choice over another, the idea that we are the ultimate cause of our actions, and we're not just sort of a line of dominoes falling over and going, oh, oops, I'm falling over. Okay, and the idea also is we can externally intervene in the flow of events without our intervention being determined by past events or fated by future events. So that's just a quick overview. So there's also a very common position in the literature called compatibilism that came out of the determinism picture. So this was even apart from any questions about a block world idea where the future already exists, or an indeterministic context. It was already a worry given the classical deterministic laws. And one of the proponents of this view is W.T. Stace, who even if we have deterministic laws and even fate, we can still have free will by just redefining it. So this is one thing that's done. You say, based on the way people commonly use free will, we just define freely chosen actions as those resulting from psychological states of the agent rather than mandated by external causes. But of course, the problem with this is under determinism, everything is uniquely caused. So psychological states are also caused by laws and events events not accessible or controllable to the agent, even if they're internal to him or her. So this leaves the basic problem unresolved. I mean, you know, why are we in charge of anything if, whether for internal or external reasons, we're sort of propelled or just dictated by the laws to make that choice? So to me, this doesn't do it. I just don't think compatibilism. It's sort of a linguistic maneuver that tells you, well, we don't have free will in that sense that I defined it at the very beginning, but we'll just say that we have free will based on what we like to think. So I don't think that works. So the other view is incompatibilism, saying that no, free will is not compatible with deterministic laws. And there's a very nice statement of this by Van Inwagen, who says, if determinism is true, then our acts are the consequence of laws of nature and events in the remote past. But it's not up to us what went on before we were born, and neither is it up to us what the laws of nature are. Therefore, the consequences of these things, including our present acts, are not up to us. So I think that's a very good way of putting it. It's just free will demands that our actions are up to us. If the laws of nature and circumstances outside our control, or none of that's up to us, then how can we say it's up to us what we do? So again, incompatibilism has two different forms. You can say, like some philosophers have done, okay, I give up. I don't have free will. That's just the way it is, okay? Or you can say, well, determinism is false, and I think we do have free will. And this was what I will defend in probably what amounts to maybe 3 more minutes. I don't know. Just do what we can. Okay, I just had a little bit on the Libet experiments. You know, I think it's such a great argument that Dr. Schurger gave about how I think it boils down to correlations are not causation. I think everyone may have seen on the internet, there's a nice graph of the correlations of number of pirates with global warming. You know, and you see as the number of pirates goes down, global warming has gotten really bad. So we need more pirates, you know. I think it's a fallacy. It's looking at only select data and throwing out other data that are crucial. And what was crucially thrown out in the Libet experiments is instances where people might have thought, shall I make my choice, lift the finger? And no, I don't think I will. Well, they didn't get anything to lock onto, so you didn't see that maybe there was that so-called readiness potential, readying the person to maybe make that choice, but choose not to. So it's really a huge fallacy, and I agree if, you know, a conference is a great opportunity to just kind of rally out there and say, no, stop saying that. It's not true. Okay, so, and just flag me when I'm out of time, whoever, because I've got too many slides here. Okay, so there's a famous argument that tries to say, well, you can say you have free will because of quantum indeterminism, but here's why I think that won't work. So the argument goes. Well, suppose we have an indeterministic universe. Let me just skip back behind this. It's just a side issue that if you want to violate the Born rule, you're going to possibly screw up other physical laws. So we probably can't do that. So let's say, we've got quantum indeterminism. Well, Sider says, oh, that's just randomness. Randomness is not freedom. And here's how I can show you, he says. Okay, so let's take Hitler. And let's describe him by a quantum state, say some ready state, okay? Got a little quantum state there. Now he's faced with a decision that Sider says can be captured by 3 different eigenstates of a choice he's about to make. And the eigenvalues of those eigenstates are invade Poland, which has a probability of 95%, invade France, which has a probability of 4.9%, or stop being such an evil guy and become a ballet dancer, 0.1%. Okay, so he says, if the argument that quantum theory leaves room for free will were correct, then my criticism of libertarianism, that means agency free will, full-blown, as being anti-scientific would be rebutted. Agent causation could peacefully coexist with quantum mechanics. In fact, though, the coexistence picture makes agent causation a slave to the quantum mechanical probabilities. So the idea being, oh, you know, Hitler has to conform to these probabilities. So in what sense is he really free? Well, Randolph Clark has a good rebuttal for this, and he points out that there's a bit of a misunderstanding about what a probabilistic law of nature is. And basically, he points out that you need a huge amount of statistics on the very, very same repeated instance of an eigenstate being, of a ready state of a quantum system being subject to a clearly defined measurement, and then you've got to have a huge amount of statistics to even begin to see whether there's a deviation from the probability law by using statistics. On the other hand, the quantum probability law can be understood as just giving single case propensities, so that, for instance, Hitler has, because of his mental illness and the kind of guy he is, has a far greater chance to pick invading Poland, but it's a single case propensity, and he probably doesn't really have to do that. I guess how much time do I have? Sorry. Oh, I got 1 minute, okay. Okay, so the bottom line is Ted Sider is wrong, and the quantum system, if you want to even try to apply a quantum system to Hitler, he's a huge macroscopic system. I can argue later, actually in my own interpretation, I argue that macroscopic objects are not even described correctly by quantum systems. But let's suppose he is. You can see his quantum state is continually changing so that if X marks the spot where he makes his choice, you no longer even know what his state is. So you don't have any reliable statistics to generate any kind of observable violation of the Born rule. So I could say why Sider might argue with me, but I'm also going to just leave you with the idea that because of the measurement problem, where we have many possibilities in a measurement, and yet one happens and there's seemingly no reason in the theory for why that one outcome occurs, I'm going to suggest that this is where volition might come in, that this is where consciousness might come in at a fundamental level, and that on some level, nature is conscious. And I'll just leave you with this final quote from Freeman Dyson. I think our consciousness is not just a passive epiphenomenon carried along by the chemical events in our brains, but is an active agent forcing the molecular complexes to make choices between one quantum state and another. In other words, mind is already inherent in every electron, and the processes of human consciousness differ only in degree but not in kind from the processes of choice between quantum states, which we call chance when they are made by electrons. Thank you very much.
Thank you. Yeah, good one. Thanks, Ruth, for trying to save free will and avoiding World War II. That was really very noble. Our next speaker, Daniel Sheehan, is a physicist at the University of San Diego. He organizes AAAS conferences on time. And Daniel Sheehan.
Good morning. Our lives unfold in time. And as a scientist, I've always been kind of amazed at how scientists avoid many of the bedrock concepts upon which all of this is based. This conference has been unusual in the sense that it's made consciousness a real science, or helped make it a real science in the eyes of the scientific community. But there are other things that it can do as well, which is to approach some of the fundamental questions in physics. We have consciousness and we have causality. In some sense, consciousness can be, if you deny the existence of consciousness, in some sense you might even be confirming it. As Descartes would say, cogito ergo sum, I think therefore I am. But when it comes to consciousness, when it comes to causation or causality, this is a concept that is so deeply ingrained in our way of thinking, in our way of storytelling, in our way of producing physical theory, that we're almost unaware of it. If consciousness is the fish, then causation or causality is the water in which it swims. And we're almost unaware of it. And in some sense, this is a mistake, because when we look at science as it currently stands, it not only admits the past influencing the present, which is causation, but the equations themselves are time symmetric, which then allows the future to affect the present as well. And this would have implications both for consciousness and for free will. The equations that you see here are those by Newton, force equals ma, so to speak, Maxwell's equations, which cover electrodynamics and pretty much explain most of the phenomena you see in everyday life other than gravity, Einstein's field equations, and the Schrödinger equation. Now, what's interesting about these expressions is that if you put in a time-forward solution, you get what we normally expect, but if you put in time-negative solutions, you also get solutions as well. So let's take an example. Consider a ball which is rolling down a hill, and in the present time, it's in the middle of the hill coming down. Normally, you'd say, well, that is caused by its past state, which is at the top of the hill. And you can write a solution to its equations of motion which go forward in time. But equally, you can have a set of solutions that come from the future into the present, which also force the present moment. And these would be what would be called advanced solutions, which are also allowed by the equations. Now, in everyday life, we have two basic kinds of phenomena. We have what are called reversible phenomena, ones which, when they go backward in time, look reasonable. And we also have irreversible phenomena. And these would be ones which have a preferential direction in time. And this would be something like things falling en masse and cannot undo themselves. And these are governed by the second law of thermodynamics. And so our general impression of time going forward is governed by the second law. So can we pierce this veil of causality with the second law? And one possible hope for this is through quantum mechanics. There are many different interpretations of quantum mechanics, as have been discussed. I have tried most of them on. I grew up with the Copenhagen, that's what I was taught in school, but it really doesn't explain much. It was the first attempt at interpreting the equations of quantum mechanics, but doesn't really have much satisfaction in it. I've tried on the many worlds, consistent histories, Bohm's theory, and I've finally settled on the transactional approach as perhaps being the most satisfying. There are many retrocausal quantum models dating back more than 60 years, and if you'll notice that in recent years there's been an uptick in the interest of retrocausal models because there seems to be a fundamental problem with our understanding of time in physics, and it is often said that the next revolutions in physics will center around time. The transactional model was developed originally proposed by John Kramer, University of Washington in 1986, based on the Wheeler-Feynman electrodynamics model from 1945. And it has a number of very nice features to it. It makes the wave function ontologically real, or interprets it that way rather than simply an epistemological creature. You have two waves. You have waves which travel from the past to the future and from the future to the past, the retarded and advanced solutions, which can be tagged for psi and psi star. The wave function has complex conjugate. And reality, in a sense, is a handshake agreement between waves going forward and backward in time. The Kramer interpretation, or the transactional interpretation, which Ruth Kastner is one of the major exponents for, has written a really wonderful book about, explains all of the major paradoxes in quantum mechanics. In some sense, quantum mechanics is defined by its paradoxes. The EPR, Schrödinger's cat, Wheeler's delayed choice, Wigner's friends, and many others. And we don't have time to go into these, but the main feature of the transactional approach is that it gives equal weight to time forward and time reverse solutions. So in seeing, for instance, the star Betelgeuse in the constellation Orion, Betelgeuse would emit a photon, let's say in 1495, about 520 years ago. It would come into the future, and then it would interrogate all possible absorbers in the future, one of which might be a molecule in the back of your eye. If your eye responds with a return solution, a response wave, then a transaction can stochastically be created, which would complete the transaction and create a handshake agreement between the past and the present. In principle, this could be done in reverse order. And so there are various experiments in retrocausation, some which are thought experiments by John Wheeler, which have been since verified by experiment, and which would, by Jacques et al. In 2007, but most retrocausal evidence comes from human experiments, ones dealing with consciousness. And a number of researchers you may be familiar with have conducted these over many decades. The timescales for retrocausation have spanned from minus 10 to the minus 21 seconds, which are basic quantum phenomena, up through human experiments, if you are familiar with presentiment and premonition, up to on the order of 10 to the 7th, so many orders of magnitude. A fundamental question then is the brain quantum in nature? And this is not really known. At the microscopic level, it most certainly is, because molecular and atomic processes are quantum mechanical by nature. At the mesoscopic level, it is plausible that there might be quantum processes. Penrose and Hameroff have, of course, championed the idea of microtubules and their quantum nature. At the macroscopic level, and neuronal assemblies, perhaps, but again, this needs to be proven. In terms of quantum lengths, the brain falls squarely within phenomena that are known to be quantum mechanical. In terms of time, it is also found to be consonant with that, and also in terms of mass. So physical laws are temporally symmetric, but reality as we see it is asymmetric, primarily because of the second law of thermodynamics. Some quantum models can pierce this veil, the second law, in principle, and allow retrocausal phenomena, and there's experimental support for this. Some brain processes are quantum mechanical, and it remains to be proven how far this moves up the chain. But I do think that this conference makes a possibility now that consciousness may not just be for consciousness per se, but could actually contribute to some of the fundamental understandings of physics at the most fundamental level, being involved in the next revolutions in physics. Many people would say that it's probably maybe a bridge too far to take up both consciousness and causality. But I would argue that that is most certainly not the case and is a mistake from the start. If we do not take up the issue of causality and retrocausality, then we're only going to cross the river halfway. We'll never get to the other side. And so I would hope that this community will take up the hard issues in science, which are free will, consciousness, and causation. And I think all will benefit from it. Thanks.
All right, thank you, Daniel. Our next speaker. Daniel, you made a mess here, man. I feel like I'm at home. Our next speaker is Julia Mossbridge from Northwestern University and IONS, Institute of Noetic Sciences. Free will and non-conscious processing. Julia.
Thanks, Stuart. So one of the things that, thanks Daniel for that beautiful discussion of retrocausality. And one of the things that people know me for at this conference and other conferences is something about presenting data, my own data and data of others about presentiment and precognition. I'm going to talk about something slightly different, but I'll bring that in here. So first I want to define, I'm going to be using the term consciousness here, and I want to define it. So I'm using Christoph Koch's definition of consciousness. So by consciousness, I mean the ability to feel something or anything. So at the bottom I have here, my consciousness is what I am aware of feeling. Okay, so I'm just gonna, that's my definition. There's many definitions. That's the one I'm gonna use. Freud says he liked to divide the everything that we're not conscious of into a bunch of aspects of mind. So the unconscious, the preconscious, the subconscious. I'm actually making a bigger, broader umbrella. I'm saying my non-conscious, so things that are not conscious to me, are exactly a complement, exactly the opposite of what's in my consciousness. Okay? The reason I became interested in all this is because of a meta-analysis, a statistical meta-analysis I did with Jessica Utz and Patrizia Trasoldi that came out in 2012, in which we looked at 26 experiments that showed physiological prediction of upcoming events. And as opposed to Aaron Schurger's beautiful work that you heard about in the plenary talk, these experiments actually had 2 future cases, and the physiology would predict the difference between the 2 upcoming cases. So that's a different scenario. So the response to this was impressively emotional, from a lot of people. A lot of people, you can see there were 70,000 total views so far on that paper, which is a lot for a scientific paper. And a lot of people, a lot of scientists felt that it had to be wrong. And that, I realized, was based on this false belief that by looking into your own experience, you could figure out how things worked. So you could figure out how time worked by watching your own experience. So the way we think about the relationship between the conscious mind and everything else, or my consciousness, I'll call it, and everything else, so my non-consciousness, is this kind of iceberg model. We know that what's in my consciousness is smaller than what's in what I'm not aware of. The reason this iceberg model ends up being false is we all think of it as in our minds. But in fact, everything that I'm not conscious of also includes this carpet, right? Except for the moment that I thought, oh, I better say the carpet, right? It includes the feeling of what it is like to live in Alaska, because I've never lived in Alaska. So it includes whatever's going on in Ruth Kastner's mind right now. That's all in my non-consciousness, okay? It's a basic division. So I've been saying this for a while, and now I decided I'm going to say it mathematically, so maybe that'll make it more clear, but if you're nervous about math, there's English translations of everything the math is on the left, the English is on the right. Okay. So imagine there's a set called C, and this is my consciousness. The things in the set include imagining from the moment of birth, bright, then comes loud, then comes want, then comes food, then comes loud. These are the things, and they go through. Imagine you can only think of one thing at a time in your consciousness. One thing appears at a time in your consciousness throughout your life, up to the last item when you die, or who knows. But anyway, let's assume there's a last item. And so the idea is that the number of things in my consciousness, my personal consciousness, is large but finite, okay? So now let's look at my non-consciousness. These are the things that are not in my consciousness. This is a set, and it includes everything that can become conscious. So let's call those like the negative integers, -1, -2, -3. Let's say -1 is the non-conscious representation of what bright is. -2 is the non-conscious representation of what loud is. And there are more than n. Remember, n up here was the number of things in my consciousness. There are more than n things in that set of things that can become conscious. Also, my non-consciousness includes things that can never become conscious. So for instance, I made a bunch of numbers that are very difficult to think of as integers, so like 0.33 repeating, complex numbers, et cetera. And those are infinite. So there's the number of things that can never become conscious include, for instance, the concept of infinity, okay? We can never actually become conscious of that. So since infinity is there, we've already got infinity in that set. So here are some basic experiences that I have that are actually driving the rest of the model. I would argue that most people share these experiences. Experience 1, things in my consciousness, things appear in my consciousness and they disappear from my consciousness. I would argue that I'm not the only person who has that experience, okay? Thing number 2, feelings of agency are among the things that appear and disappear from my consciousness. Okay, so sometimes I want something, and sometimes I do something, and I have the experience of wanting and doing that. Experience number 3, I am not conscious of the mechanisms that determine which particular experiences show up in my consciousness, nor the mechanisms that determine when these experiences either leave or appear in my consciousness. Now that one needs a little explaining. It comes from phenomenology. So scientists who actually ask people what's going on, turns out that they have found that people are very good at reporting what their experience is. If you put, for instance, an ice cube in someone's hand and rate the pain that they're feeling, there'll be a very consistent scale across people over time and across people about how that pain changes. But then you ask them, how did you feel that pain? And they have a bunch of different answers. So my point is, the reason we have consciousness conferences like this one is that people have a bunch of different answers about how things get inserted into consciousness. So the reason we also have funding for neuroscience is that you can't just look and say, let's see, I'm seeing the color green over on the exit sign. Oh, right, that's because that neuron is talking to that neuron. You don't have direct access to these mechanisms. You're not conscious of them, okay? Or at least I am not, I'll tell you that. So my consciousness does not contain the mechanisms that select and change the contents of itself. It's a set that includes a bunch of items that does not contain any mechanism to change what those items are. But the things of which I'm not conscious, or my non-consciousness, does in fact have to include the mechanisms that select and change the contents of consciousness by default, because those mechanisms have to be somewhere, and I'm not conscious of them. And over on the left, I've put in a CH function and an SL, like a change and select function. Notice that the selection function, which decides what goes into consciousness, or actually what gets fed into the change function, which the change function is what decides what goes into consciousness. The select function could be deterministic, like I've written it, or one of these conditions could be flip a quantum bit. It doesn't matter, right? So the point is, none of that is in consciousness. That's the basic point. So, my consciousness cannot have free will because it does not have the verbs. It doesn't have the mechanisms to select and change the contents of itself. My non-consciousness might have free will, I don't know, but it does have has a shot at it because it contains the mechanisms to select and change the contents of itself as well as my consciousness. So the choice ends up being that we could potentially have actual agency, but we have to alter our sense of self to include the non-conscious, or we actually have no actual agency, but we keep the illusion of agency by saying that we are just my consciousness. So what I'm saying is, when we ask the question, do we have free will? A lot of people concentrate on what is free, what is will. I want to know, what is we? Okay? Are we, my consciousness, which is this very simple, frankly, this thing about one idea at a time is not far from the truth in terms of perceptual studies. It really looks like when people think they're thinking of two things at once, they're actually just alternating quickly. So assuming consciousness is one thing at a time, or even 2 or 4 things at a time, still, if it doesn't contain the actual mechanisms to change itself, then our non-consciousness, which is everything else except for our consciousness, is in fact what has free will, if anything has free will. Does that make sense? Good. Okay, so now given that situation, let's come back to these things like presentiment, precognition, retrocausation, or anything that, frankly, anything that surprises us from empirical data because it doesn't match with our conscious experience. Should we be surprised if our non-consciousness has access to actions or events that seem to be in the future according to consciousness? My consciousness is a list of items. My non-consciousness is this huge description of all these events and conditions under which things will change in my consciousness. Who do you think we should trust? Which system has more information about what's going on? It's not our consciousness. So that's my basic point. And before I say that, I just want to say, this is a challenge for Aaron Schurger. I did this experiment which is essentially equivalent to having 2 tones, 2 different kinds of clicks, like a high and a low click. And in that situation, you can actually differentiate the brain activity that comes prior time lock to the click. I did this across 40 people. And so that would be the experiment that I think that would be really interesting to do. So I want to say thanks.
Thank you. Do you have slides? Ron, do you have slides? I know. Okay. Our next speaker, thank you, Julia. Our next speaker is Ron Gruber from Stanford University. In psychology, right? Psychology?
Stanford University Medical Center.
Okay. Stanford University Medical Center, Free Will, Lessons from the Flow of Time. Ron Gruber.
Thank you, Stuart. Good morning, ladies and gentlemen. I'd like to share with you my experience from the flow of time and how it relates to free will. For us, the flow of time has 2 levels. The lower level, as you see here, exemplified by a volcano, which is happening, the experience of flowing, sound, color, everything. But then there's an upper level, a cognitive phenomena that objects in ourselves seem to pass from the future to the present and fade away into the past. Lesson number 1 from the flow of time is that definitions are critical. Typically, an illusion is something, it's either a percept or a cognition that is contradicted by physics, assuming physics is correct. But on the other hand, as Susan Blackmore pointed out, illusion is not something that does not exist, such as a phantom. It may be something that is not what it appears to be, such as the blind spot in the eye. It would be black. The brain makes it look like the brick wall, as you see here. So it's an illusion, but it agrees with physics. Now, regarding definitions being critical, you should know that the flow of time and the passage of time have always been conflated. And that's too bad, because the passage of time is really a physical word and refers to cosmologic theories. For example, the Ellis evolving block universe, where the Einstein part of the block universe is there, but the future part is quantum nature and happens and appears, and in that sense it flows. But that's not the same thing as cerebral flow. So flow is not equal to passage. Well, what implications do we have for free will because of that? Well, there's a cognitive free will, a conscious free will. There's a physical free will, really the delayed choice double-slit experiment. And there's no time for me here to tell you about that, but that's the crux of the argument for the free will debate. And I think it might be said easily that will and choice may not be the same thing, and we're talking against each other. This comes to light when you think about the enigma of quantum theory, which is, let's assume for the moment that all brain behavior is directly or indirectly controlled and predictable, deterministic. But then the delayed choice double-slit experiment indicates that there is a choice, or at least a fork in the road, willed or not, and as a result of that fork in the road, as quantum physicists will tell you, we're predicting the future event by acting in the present to make a selection that affects the past. And if you're affecting the past, determinism is upset, and therefore you do have free will. And here's your enigma. Lesson number 2, the lower level flow of time is backwards in time. Now, current well-known backwards in time phenomena include examples of post-diction, such as apparent movement. You'll see here 2 red spots. The upper red spot moved over. The motion is apparent and an illusion, of course. The lower one didn't, because the object is not the same and not clearly. The brain makes a decision after seeing the red spot. That's when if you don't mind the expression, loosely speaking, the perceptive motion is painted on retroactively. But there are some new backwards in time phenomena. For example, this toasting of bread. When the interstimulus interval is anywhere between a second and 3 seconds, a human being can tell you that they saw something happening. It's a percept. It's similar to dynamic change that Yokosawa has demonstrated with the rotating bed phenomena. And this is a very real phenomenon, but it occurs over several seconds. You can see it in multiple modalities. It occurs with a bug crawling up the forearm. That is, when the interstimulus interval can be anywhere from a half a second, and in a few people up to 7 seconds. There is that phenomena, that modal perception, modal completion of happening. When we look at the curve of it, you would see that we can measure it out, and although most people don't see it, this phenomena of dynamic change at the 3-second level, some people see it far out, and clearly it has to be backwards in time, just as it is for motion. That's a long backwards in time phenomena. Now, this rotating wheel in reverse is what was used by Van Rooyen and Koch to demonstrate that all visual perception is discrete and not continuous. Why is that important? Because the gap for motion has to be filled in backwards in time. And we're talking now about all motion, not just a simple illusory experiment like the phi phenomena. We're talking about all motion. In fact, the gap for stationary objects is filled in as well. And let me demonstrate this to you in a 1-minute video that we submitted to the National Illusion Contest just for fun, which will tell you everything about what Koch and Van Rooyen did.
When two alternating disks are brought together and overlap, the colors do not combine. When completely overlapped, the disks flicker. As the frequency is increased, the colors do appear to combine. And when completely overlapped, the disks appear continuous. Just one disk, an illusion of visual persistence. It has been said that if the world stands still, we manufacture motion to perceive it. Similarly, if the world consists of separate and distinct events, we manufacture our own continuity to perceive it. Evidence is strong that perception is separate and distinct with a rate of about 10 snapshots per second. This suggests, for example, that a yellow traffic light actually flickers. We fill the gap and it appears as one continuous light. This illusion is one way the brain can fill in the gap of every stationary object observed.
So this has been a very interesting phenomena. And let's, though, however, move on to the implications for free will. You know, conscious updating for a backwards in time phenomena does seem to be periodic. At least Chakravarthy demonstrated that. And current mechanisms for post-diction involve correlations with known brainwave frequencies, such as alpha theta. However, there are really no known mechanisms from the brainwaves that would account for what we're seeing with this backwards in time phenomena with dynamic change or modal completion of the happening percept. So we don't have a phenomenon to account for except what Hameroff, Penrose in the orchestrated objective reduction theory came up with. We have an opportunity to bring quantum mechanics into the picture. Now, I borrow this from Stewart's article. I mean, most of you have seen it, or you should have seen it, showing how in the conventional view, the Orwellian revisionism view, this is how the brain, after the fact, puts the information together. But the quantum mechanics view allows us to do something, if you don't mind the expression, backwards in time, so that there is free will at the moment of observation. And so what I've done is taken the liberty to modify Stewart's schematic by putting in these long backwards in time phenomena and show that if you tried it with a non-quantum approach, it wouldn't be quite so easy to explain this tremendous duration of time, how we're going to do that. But if you use the quantum approach, as he has used for free will, then you can see, and it doesn't have to be his particular, I mean, that of Stapp we might use, Sheehan's or Kastner's, but the point is a quantum explanation can be extraordinarily helpful here to explain the long backwards in time phenomena. So in summary, what did we learn from the flow of time? One, that defining terms is critical to resolving the debate about the flow of time. We have to be careful about free will versus free choice and be sure we don't mix them up. Number two, keep in mind that the evidence now suggests that the flow of time, at least the lower level, is indeed backwards in time. And as such, if it's backward in time, the quantum theory may be a better explanation for it, just as it is an explanation for conscious free will. Thank you very much.
Thank you, Ron. You don't have slides, right?
No slides.
Okay. Our next speaker is Martin Nowakowski from the National Quantum Information Center in Poland, talking about quantum entanglement in time. Martin.
Hello, everyone. It's a great pleasure for me to be today with you. Yeah, thank you. I was given a lecture on Tuesday about the phenomenon of quantum entanglement in time. So if you are interested in technicalities and details from quantum physical perspective, I invite you to read the papers of mine and of my quantum group. We have only 10 minutes here, so it's not much time, but if we could fly at the photon of light, then we could have infinite time. I believe that you would like to have infinite time for your life. So I will ask the same question in 10 minutes. I will briefly present the concept of quantum entanglement in time. Quantum entanglement is a very interesting phenomenon, which is a resource for modern quantum information theory and for quantum computation. But to date, we have been talking mainly about quantum entanglement in space, because when we think about applications of quantum entanglement, we talk about quantum entanglement in space. We talk about correlations between particles, between systems in space. And quantum entanglement, this is this spooky action at distance. What is important when we talk about quantum entanglement in space, we have to remember that we cannot send signals faster than light. This is the grounding rule which quite often is forgotten by people. That is a very important point. What is interesting about quantum entanglement in space is that when we have two particles, we can imagine that the first particle is in galaxy A, the second particle is in galaxy B, and the particles are correlated in a magical way. If you will ask somebody, what does it mean, what quantum entanglement is, and somebody will try to answer this question to you, it means that he doesn't understand that. Because there is nobody actually in the world who really understands what is happening here. We have mathematical representation of that. For quantum entangled states, we can talk about representation in tensor Hilbert spaces. The problem is with the reduced states of subsystems for which we can assign only density matrices. We cannot assign a pure quantum states. So this is what mathematically differentiates entangled states from separable states. So this is another story. Coming back to this concept or example of two particles between two galaxies, we can assign one state, one common state to both systems at once. And this is the critical point in the whole story, that we can assign a pure state. This is what quantum physicists are saying. We can assign a vector state from a tensor Hilbert space. So we can say that there exists a state of the two, but there is no independent state of any of the subsystem. So this is about this quantum entanglement in space. We started to ask a question about, can we really also ask such questions about entanglement in time between the particle and its future states? So we talk about correlations and quantum correlations between a particle at a given moment of time, whatever that means, because this is another story, and its future states. The problem from physical perspective was with finding appropriate mathematical representation for that. So Daniel and you also referred to this backward signaling and two-state vector formalism by Yakir Aharonov and Lev Weidman. This is one of the proposals that we have in quantum physics, and we do not have actually anything else. So the problem was with the tensor algebra. We started to look at a model of consistent histories. The consistent histories approach is quite an old approach. The issue with that is that consistent histories approach actually contradicts non-locality. And that is something very interesting here. So during actually the recent 2 years, the group from MIT, Frank Wilczek and other people, they proposed actually some modification. I was working on the same subject of suggesting entangled version of consistent histories approach. So we started to analyze mathematical structures for that, and we discovered that we can use a similar tensor algebra for representation of quantum entanglement in space, and we showed that we can represent quantum entanglement in time in similarity to quantum entanglement in space. So at this moment, I'm very happy for that, because we are at the moment where we can now say, yes, we have the phenomenon of quantum entanglement in time. We have a proposal of mathematical, it's not ideal, there are still some issues with that, but we have a proposal of mathematical representation for states which are correlated in time. And we can, that is the recent paper by Frank Wilczek from MIT from February, we can also suggest such some experiments in laboratory distilling actually entangled histories and entangled states of a particle, let's say of a photon, in Mach-Zinda interferometer. So that is something very, very, very interesting. I proved in my paper from April, so it was actually during this month, I published that. The results were presented also in Turin in previous year on a conference about time, that quantum entanglement in time has monogamy properties in similarity to quantum entanglement in space. So there are many similarities between quantum entanglement in time and quantum entanglement in space. However, these are quite different phenomena, and this is something important, something very, very important, crucial here, that we do not have 100% analogy between the two phenomena. What is also very important, and I would like to emphasize that, we cannot signal in accordance with our modern knowledge, current knowledge about that. We cannot signal from future to present. So I'm a little bit suspicious when we are talking about backward signaling, because this is the same as we were talking about signaling in space. We have to be in accordance with general relativity theory and special relativity theory. We have to look at the light cones in a space-time when we talk about signaling in space or signaling in time. But there is entanglement in time. There is entanglement in space, although we cannot signal. And I was talking about that on Tuesday, that it might be an explanation of the Libet experiments results. And I think that we have also equations, these Leggett-Koch inequalities, which can be used for verification of laboratory results in case of a Libet experiment. However, we have to have a good objective data which have some kind of probability distribution that we can compare between time B and time A. So I invite you to look into these papers and this new phenomenon, because it gives a couple of very fundamental consequences. One of the consequences for me is that maybe it's even a philosophical consequence, is that actually the field, or the quantum field, is in some sense eternal, because it is always correlated with its future states. So we are coming to the point where we can talk about eternity, actually, of a quantum field. And I will come back to my first question. So if we could fly at the photon of light, we would have infinite time. That is in accordance with general relativity and special relativity theory. We know about that. So, but we do not have infinite time in our lives. On the other hand, we are sitting in our heads. What is consciousness? We are sitting in electromagnetic fields, which is a quantum field. So it's a field of quanta. It's a field of light, actually. This is what quantum field theory says. So we are sitting in light. So why we don't have infinite time? Thank you.
I can't resist a comment, Martin. So it's true you can't have signaling going backwards in time, but by the Alice Bob paradigm, you can have correlations going backwards in time. And that's good enough, I think, if you have a classical channel to have an effect. The point of all this is if you forget what Aaron said and take the standard view that the readiness potential is when the unconscious begins to plan or initiate the action. It could be that the actual conscious decision to move could send a correlation backwards in time to cause that preparation to begin, thus rescuing conscious free will, perhaps. So having said that, let's move to our last panelist, Matti Vuorre from Columbia University, 5,000 years without free will.
Thanks very much. Before I begin, I'd like to thank the organizers of the conference for putting together the panel and then making the mistake of inviting me to be on it. And then I'd also like to point out that I also just recently found out about Aaron's results and model, and it's just my humble opinion that it seems to be perhaps one of the most significant results that we have pertaining to this empirical road to investigating free will. So that was a really interesting presentation. So I want to talk about, instead of 50 years without free will, I'm going to talk about 5,000 years without free will. And I've talked about this with my philosopher colleagues in the past, and they tend to comment, they quote Van Halen, and they say, I ain't talking about free will, because instead I'd like to discuss the pragmatist's guide to studying free will. What do I mean by this? Well, many of you are probably familiar with Julian Jaynes' idea of the breakdown of the bicameral mind. And this comes from his 1976 book, in which he suggests that the prehistoric peoples heard voices in their minds, in their heads, and obeyed these voices, such as go and drink wine or whatever, and they would do these things, but they didn't realize that it was themselves generating these voices inside their minds. And then after the breakdown of the bicameral mind, people became to realize that it's themselves generating these voices inside of themselves, and then realizing that they themselves are conscious agents experiencing free will. And this is the point. People began experiencing themselves as conscious agents. And I really want to focus on the experience, because that seems to be something that's, that we all can agree on. We can experience, we do experience free will. However, I don't comment on the veridicality of the phenomena of breakdown of the bicameral mind. The point is that free will is an experience. Wittgenstein, in Philosophical Investigations, famously asked, what is left over if I subtract the fact that my arm goes up from the fact that I raise my arm? You could come to several conclusions. You could have several different answers. One of them is that what is left is some sort of a subjective sense of agency, an experience of being the lifter of the arm. And I will talk specifically about how we could empirically, or how we empirically do study this experience, this sense of agency. And similarly, we can also talk about attributions of agency to other agents, objects, people in the environment around us. And these together constitute what I'd like to call the pragmatist's way of studying free will. So how do we measure the experience of will? Well, this relates specifically to Benjamin Libet's experiment. So we can study the subjective timing of actions. So what we do is we run the usual Libet experiment. People focus on a clock that rotates quite swiftly. They press a button at a time of their choosing, execute their volition, one might say. And there's a slight modification here. Sometimes, on some trials, the button press causes some kind of an effect, such as a beep. And then the subject reports when these events happened in their subjective awareness, meaning where they thought that the clock hand was. So we can construct an objective timeline of events. And then we can contrast different kinds of trials. And the most important contrast here is between trials where these two events happen together, so the actions cause the tone, versus trials where the actions happen in isolation or the tones happen in isolation. So in these kinds of operant volitional trials, people experience that their actions and those actions' effects occur closer together in time. That is, they become bound together, chunked in subjective time, and this effect, when it was discovered, was called intentional binding. And this constitutes a really interesting empirical measure of the subjective sense of agency that specifically relates to what we know about causality in general, namely the structure that events have to take in time for people to experience causality. So intentional binding is a really appealing empirical measure of the sense of agency that I hold is really one of the few empirical ways that we can study free will. It's sensitive to the action-outcome contingency, meaning that it changes with relation to the probabilities that your actions cause outcomes. It only happens to voluntary actions, not for passive movements of the body, such as if you give transcranial magnetic stimulation to the person's head, causing hand movements that cause actions. You do not observe this effect. It reflects an online compression of time between actions and their effects, and this is what I talked about extensively on Tuesday, relating to my work with visual illusions, assessing this phenomenon. And I think it answers Hugo Münsterberg's question. So Hugo asked this some time ago now. In what way must sensations be combined to produce the feeling of active will? Now, we have some intuitive answers to this question. One is that, well, there has to be a coherent timeline that accords to the general principles of causality, but it also seems to be the case that the brain perhaps predictively generates or modifies the subjective timing of events to keep up this experience of agency. So this is one way that we can study the subjective experience of agency. We can also study attributions of will, so how people think about other objects in the environment having free will or not having free will. And one key quantity here is unpredictability. The key result here that I want to mention is that other agents' actions seem voluntary to an observer when those actions display functional unpredictability. What does that mean? Well, in simpler terms, when those agents' actions are unpredictable but not stupid. That makes sense, hopefully. So a thermostat has pretty sensible behavior according to the rules of the game that we set for it, but they're not very unpredictable. Vice versa, if you have a random number generator, you can't really say that it's a very smart system in some sense, but it's highly unpredictable. Also wouldn't have, we wouldn't think of it as a volitional system. Now I'm just going to quickly go through some empirical findings from Neuringer and Jensen relating to this phenomenon. So they asked human participants to observe on a computer screen various different types of virtual agents. And you can think of these virtual agents as being characters on the screen that do some kind of gambles or play slot machines, for example. And some of these slot machines reward the actors. And the human subjects see these rewards as the virtual actors changing color. So that, for example, they go green, and then the human participant sees, oh, this agent was rewarded. So you can kind of see how rational the action of the virtual agents is by assessing how often they get these rewards, for example. Now what they constructed these actors according to different sorts of algorithms, and I'm not going to go into the detail here, but the idea is that the algorithm that generates the highest volition ratings in these observers, so people think that these virtual agents have the most free will or are the most volitional agents, The algorithm generating those agents is the stochastic matcher algorithm, which means that the virtual agents distribute their responses to these different, let's say, slot machines in proportion to their rewards. But note that this is a stochastic algorithm because they distribute the proportion in accordance to the rewards. But you can have algorithms that always know, for example, where the reward is. These are rated the lowest on this volitional scale. We don't care about this right now. The bottom line is that even though the stochastic matcher is reinforced less often, it seems most volitional. So this kind of just highlights the fact that we think that agents are volitional when they're unpredictable but not stupid. So these are just the two lines of empirical inquiry to agency on the inside and then on the outside as well. So 5,000 years after the Jaynesian breakdown, we, the pragmatists, have exciting and rigorous methods for studying experienced and observed agency. Thanks.
Thank you very much. We'll ask Aaron to come up and take some general, where was the lady I rudely cut off before? Let her ask the first question of Aaron, please. And I thought that was really an excellent panel. As you might know, Libet did also sensory experiments where he showed what appeared to be backward in time referral of subjective experience. Go ahead, Steve. But these were overshadowed and ignored due to the volitional experiments. So,
Thank you very much, Eva.
do you guys have a mic?
So, I will read a couple of sentences from this book.
Use the mic.
So I will read a couple of sentences from this book, The Science of Consciousness. And this refers to that slide with the flu, coming down with the flu. And also, in the meantime, about the problem with Hitler. And I would like to have your feedback, if you have any. People with negative attitude are enslaved by their circumstances and behave as puppets on a string. Their conscious minds are employed as public relation agents to constantly explain away previous behavior. Free will is only possible for a satisfied, trusting, calm, or happy mind where there is no emotional incentive for change. So do you have some
That's a tough one. Anybody else want to try before I?
Just say you're
So
great.
what I mean by that this is negative attitude is when you are coming in your slide, you were showing that brain picture, that it is getting weak, or the immune system was affected. So we are talking about different things, but as an analogy, we are talking about negative attitude, or we are talking about a negative, an affected immune system.
I can just respond just for my own personal experience, I guess, is that I certainly feel like I have more free will, more volition when I'm in a happier state. It certainly feels that way, subjectively.
So do you think Hitler, if he was happy, would he consider, would there be better chance for him to become a ballet dancer instead of?
That wasn't from my talk. That was yours. So.
Well, he'd probably need some serious other inputs into his nervous system, I don't know, to get to that point. But I think you make an interesting point that if I could just mention I was once getting interested in Gnosticism. It's just, as a philosopher, I like to study different modes of thought. And I don't know how many of you here have read works by Peter Uspensky, but it comes out of the Hermetic tradition. And his big thing was, we are asleep in our own lives. And that to the extent that, reaching enlightenment means that you wake up, and you stop being asleep and subject to these other forces that he talked about in the world. And I think that argument could be made that if you really are kind of asleep in that sense and not fully conscious and not feeling well, all the things that go along with that, then you're not in a position to exercise the kind of free will that I think is really the real free will, whereas you're really in control of your volitional capacity rather than being pushed around by other forces. So,
Thank you.
I think we have two levels of discussion here. The first level is who makes the decision, the consciousness or the non-consciousness? But I think if we assume that consciousness and non-consciousness are both physical systems, I think this question is irrelevant, because the important question is, are physical systems deterministic or undeterministic? And I agree with Ruth that if they are deterministic, there cannot be a free will, because everything is deterministic. So it leaves us with the option that the system must be indeterministic. But free will requires control, and indeterministic events cannot be controlled. So eventually we don't have any chance of free will in a physical world, is my assumption.
So I guess, that actually is resolved, I would argue, and I indicated briefly, because of the idea that indeterminism is not equivalent to randomness. And at Clee Irwin's talk, he pointed this out too in one of the concurrent sessions. And the big problem with quantum theory is there is indeterminism, but the theory also never gives you any reason. There's nothing in the theory that says why one event actually happened. And that's kind of the measurement problem. Well, the theory just gives you a bunch of possibilities possibilities for different outcomes. And you actually need some kind of input into it to make anything happen. This is sort of Leibniz's principle of sufficient reason. So if we think that principle is true and does hold that if you don't have some sufficient reason for an event to occur, then you can't really explain why that event occurred. And this is, I think, an opening for volition.
But you cannot control it then, consequently.
Well, I would say you can, because you're saying, and I don't have a detailed model for this or anything, but presented with those different choices, you say, I'm choosing that. And, at the very fundamental
then it's deterministic again.
What's
if you
that?
choose it, then it's deterministic, because you, based on reasons, you choose something, then it's deterministic. For indeterministic,
then you
control.
are the uncaused choice, the uncaused cause. There's no prior, the quantum indeterminism makes it such that there's no prior deterministic cause on your volitional choice. So that your volitional choice is a true intervention and sort of it's a primary, that's the whole idea of agent causation, is that you are a primary uncaused cause. And you can't really find room for that in determinism, I think, but with indeterminism, there is room for it, especially since the set of outcomes sort of begs for someone to go, well, which one of us is going to happen? So it's a very subtle and complicated issue. We could talk more. Yeah.
Over here, please.
Okay. My question mainly to you, Julia. Yes, you told that a personal consciousness could be only finite. But maybe you know George Cantor, who created set theory, and even before him, there was the idea that the infinite could be two types of infinite. One is actual and another is potential. So I think personally that actual infinity could be conscious. So through my conscious, I can embrace not only finite but actual infinite things. What do you think about that?
That could be It doesn't matter for that model?
Yes, because free will come from infinite.
Yeah, so the reason that in that model I've got these two sets, one which contains the mechanism, or the mechanisms to select and change the contents of consciousness, and the other that doesn't, is because that's based on all I've got to go on, which is human experience. That's all anyone has to go on, right? And so it's our human experience. You can say you can grasp infinity, but do you know exactly what's going on in your brain and in your mind, or whatever, however you conceptualize those events come to you? Do you know exactly what's going on? Maybe. You might have a story about that. But does that match with this person over here's story? No. But we all basically agree. I would say 99% of the people in this room agree that they're in a room. And they have the experience of being, well, not that they're in a room, that they have the experience of being in a room. And they have an experience of looking at the stage if they're not asleep or whatever by now. And so it seems to me that it's self-evident that the ways in which the contents of consciousness are changed are not in the contents of consciousness. And so, yeah, that can be, let's say it's infinite, fine.
Okay.
But our empirical observation that is shared across, I think, everyone I know, is that we cannot agree. I mean, that's why we're here. We can't agree on how consciousness shifts and changes and works. The reason we can't agree is we don't have direct experience to it.
Yeah, I mean, can you agree that conscious can include unconscious? And in this case,
no,
like enlightenment will happen.
I mean, those are
example.
mutually exclusive. All right, so according to my definition, they're two mutually exclusive things. It is the exact complement, not my non-consciousness, is the exact complement of my consciousness. So by that definition, it can't include the other, you see?
Let's move over there. Let's try to keep the questions and answers brief so we can get through the question line, please.
This is for Ron Gruber. You gave many really wonderful examples of retrocausal, things that look like retrocausal effects. All of them except one have very simple neural correlates that have been explained. And the one exception that has not yet been explained is that wagon wheel illusion, the Koch thing, where there might be a temporal 10 hertz thing that is produced that wagon wheel. Would you agree with me that all the others except the wagon wheel have very simple explanations, neural correlates?
Well, I agree with you to some extent. The wagon wheel illusion was done, as you know, by Koch and Van Rooyen to show that there is discrete, non-continuous perception. But it's pretty obvious that then that's easily explained. I think all the others, the short duration, the short backwards in time phenomena are all easily explained because you're dealing with tens of milliseconds and hundreds of milliseconds, and you can relate that to brainwave frequencies, as Van Rooyen did. But you cannot explain the very dynamic change. Yokosawa showed a bed to a participant, and 1 second later he rotated the bed, and the participants all said that they could see the change occur. That had to occur backwards in time because they couldn't say that until they saw the second stimulus. Now 1 second, 1,000 milliseconds, is very hard to explain with brainwave periodicity, but it's much easier to explain with Stewart's quantum mechanism. And I didn't realize this, quite frankly, until Stewart gave me the assignment to deal with free will, because my area of expertise is in time, and I never knew much about free will. And Stewart, I'm grateful to you for doing this. But it really set me up to start thinking about the fact that, ironically, the flow of time is backward in time. I think this would appeal to quantum physicists.
That's the one example that I've never heard of, so I'll find out the reference for it. Thank you.
Yeah, this is a question for Aaron Schurger. Thanks very much for your valiant effort to save free will. I personally think it's all an illusion, but you were mentioning the potential that's coming from, the afferent potential that's coming from the outside back to the brain, which, if I understand that correctly, gives ramps up the stochastic potential towards threshold. And this is necessary for sort of, the late perception towards free will. Do you think that has any implications with altered states of consciousness and also pathological states such as schizophrenia and autism, where reports show that there's a decrease or a attenuation in the sense and the illusion or the sense of free will because of potentially problems in the predictive coding and the matching of the efferent and the afferent signals?
So I'm aware that there's this literature on that, and you see, from my understanding, differences in the feeling of agency or volition. It can be different in those different patient populations. In the work that I presented today, I didn't touch at all the topic of volition, of the feeling, right, of being.
Right, that's what I mean, yeah. The feeling of it. Yeah.
So I am working on an extension of the model that I introduced today that accounts for certain behavioral variables having to do with the feeling of being.
And the feeling is probably coming from a matching of the incoming and the top-down and the bottom-up signals, do you think?
Yeah, if you're talking about forward models and comparators, yes. So something like that. Does that answer your question, or?
Kind of, yeah. Thanks.
Okay, I'll make one point is that I never set out to save free will. I don't think I have. I set out to just get to the bottom of that whole thing. So.
Hi. Is this on? I came here to actually comment on sort of Eastern ideas about following what Julia was saying about free will has to do more with sort of your identification of yourself, and this idea that in the regular waking consciousness aspect of our being, we are associating our sort of ego self with the world. And in that sense, what you call the conscious mind is this mind which relates itself to the external world as not being able to cultivate free will to the extent that once, maybe through meditation or certain altered states, you can access the unconscious mind. And so there's different layers of the unconscious mind. Getting sort of the penultimate stage is the stage called the Vijnanmaya Kosha, which is basically this idea of discernment, and that's where kind of free will comes in. And the discernment happens between your identification of whether you are this or you are that, where that means you're that everything. But maybe you can comment on that. But I came here and I've been clashed out with.
Please ask the question and be brief. Okay, please.
Well, that's the comment. But there's another comment that I want to make, which has to do with the brain waves.
That's okay.
It's brief. I've seen a lot of people talking about brain waves and how that relates to, brain waves are basically a measure of within the frequency range that EEG can measure. So there's also other frequencies that we may not be able to measure that neurons are responding. This is sort of the two comments prior, that our brain could still respond to certain things at those frequencies. So.
Depends on the sampling rate of your equipment.
Exactly.
Yeah.
I actually agree with him. Over here?
It's often cited that mathematics is the language of nature. I strongly disagree. I think it's just a man-made language, which is currently the most accurate we have to describe the nature of the material, measurable aspects of the universe. And it uses the logical hemisphere of our brain. The ancient Egyptians, for example, they had hieroglyphics, which used the creative part of our brain, and it was a far richer language for emotions and for explaining like spiritual, dreamlike states. I think in order to tackle the problem of consciousness, we need a new language that uses the creative part of our brain. And I think
Can you ask a question, please?
I think we need to look to nature to gain inspiration, possibly like the gene regulation. And I think if we put a probe into a black hole, it will make mathematics redundant. What do you think about that?
We all agree.
Aaron,
Yes?
Go ahead. Go ahead, respond.
Respond.
If you like to.
Oh, I liked it. I don't know what to say, though.
No, we agree.
Okay. I have a specific question for you, Aaron. Is it a valid takeaway from your talk that the ability to make a free choice depends on an opportunity for that? That opportunity is a time-varying commodity that becomes present or absent given the statistics that you cited as correlated with brown noise. But you have to have that opportunity.
Yes. So I wouldn't say that. No. But that has been said before. I think Eccles talked about that. So Popper and Eccles talked about there being very similar to the idea that I described in my talk. There are background intrinsic fluctuations, except that they took a dualist stance and said that the fluctuation is something of which the immaterial force then takes hold in order to produce an action.
Thanks.
Mm-hmm.
Oh, hi. I would like to ask our panelists how many of you would entertain the idea that we are living in the matrix?
I've entertained the idea.
Yes, believe.
It seemed to me that if we are if our universe is a processing output of a computer, and all those problems we have been discussing can be resolved. For example, time, the past is basically processed data, and the future is unprocessed data, so it cannot be asymmetric. And the present moment is special because it's the moment where the calculation happens. So that's why it makes so special. And the time cannot flow backwards because computation is irreversible. So all those physics problems we can resolve by accepting that we are living in the virtual reality. I mean, the free will, the decision-making, causality is also an output of a program. Yes, okay. So it's entanglement. I mean, entanglement is determined by a program, which doesn't matter what's the distance between them.
So, so your question is, do we live in the matrix? Is Carrie Ann Moss there?
Yeah, I mean, the problems time you raised can be resolved this way.
Well,
do you agree with that?
Well, when you make a statement like computations can only be done in one direction,
yes.
You're already presuming your answer. So I think I would just object to the way the question's phrased.
Okay, we're running short on time. Let's take one question over there, then two more over here, since these guys have been waiting a long time, and then we have to break.
Okay,
Sorry.
the microphone's gone down.
So one there and two there.
Okay, I just have to put some points. It's quite simple and quite fast. BBC Horizon some years ago came out with a documentary called The Secret Year, and in the end of the documentary, Du Sautoy, who is running the documentary, went to John Dylan Haynes at the Bernstein Center for Computational Neuroscience in Berlin, and he made a specific, quite simple experiment in which he was put in an fMRI machine and given two options to choose between two buttons. And apparently, in between 6 seconds and right now, for what I've read last weeks, to 10 seconds, they can computate neurologically which button he was going to decide. So it's more than just one simple question. I think it's more an open question for all of you and goes forward in what we're discussing here. And at this point, Du Sautoy goes for so that means that we don't have a decision point. And the researcher actually answers him in a different way, explaining that, well, basically, at some time, you could choose, or took a decision for between it. But after that, you just can't anymore. There's just one direction. It's already made, already collapsed or something. So I would like to hear what you guys can say about it.
Okay, thank you for the question. The question is very, very, let's say, complicated, I would say, because this relates to the free choice subject. And in quantum mechanics, we have an assumption about the free choice. This is an assumption. So we don't know what does it mean to choose freely, actually. If we assume what Lev Weidman believes in, that we live in a multi-universe, then you are correlated with information which might be stored in different universes. But we have no tools to check that. So this is a matter of science fiction at this moment, actually. Okay. But I think that maybe in a couple of years we will have some tools in our hands that we could use to analyze such data in laboratories.
Okay. Thank you.
So I think the studies you're talking about was the study by Soon et al. in John Dylan Haynes' lab.
Yeah.
So it certainly is true that one way to convince people that free will doesn't exist is to predict their behavior in advance. But one has to be very careful in evaluating evidence of that sort because it is fraught with problems and the devil is in the details. And usually it's the details that we miss. In the Haynes study, consider that, so they were able to predict what choice someone was going to make 8 seconds beforehand, I think was the rule.
Around that much.
Around about. But they were able to do that only slightly better than a guess.
So it's like 98%.
58%, 58 or 60% correct, at least in the studies that I'm aware of. Mm-hmm. So they had a little bit of an edge. So the question I'd like to pose is, what would it mean if they couldn't predict somewhat what the person was going to choose a few seconds later? That might mean that their response was just coming out of nowhere, which we know isn't the case. When you make a choice, the choice comes from your brain, and your brain is not completely removed from the states it was in 5, 6, 7, or 8 seconds before. So it would be strange for them not to have been able to predict a little bit what the person was going to choose those seconds in advance. But the detail that matters here is literally the accuracy of their classifier, 58 or 60% correct. If the classifier was making those predictions 8 seconds in advance at 99% correct, we'd be having a very different kind of conversation.
I honestly remember that the data was like 98%. He says that in the movie, actually. But, well, he was talking about specifically 7 seconds before. But I've read it can go to 10. And for what I understood, it goes down of how much you can predict in terms of percentile. So there is a point where you can really predict what is going on. And, well, 98% is big. I know it's a lot bigger than 68 or 58.
Yeah. So the particular documentary you're talking about, I'm not aware.
Give it a look. It's amazing.
Okay.
Thank you.
Thank you.
Yeah, I'd like to congratulate Aaron for his wonderful explication of Libet's enigmatic results. If I remember correctly, Libet also found that even though the conscious mind didn't have free will, it could veto an intention to act. Which I take to mean that we do not have free will, but we do have a free won't. But in any case, do you have any, have you done any experiments to show vetoing of conscious actions?
I have not, but in fact, now that we're on the subject of John Dylan Haynes, there's a recent paper from his lab that does, by, I think the first author is Schulze-Kraft. It's a very interesting paper. It's called The Point of No Return in Vetoing Self-Initiated Actions. What they found was that the roughly 200 milliseconds mark was actually the point after which you could not veto an action. So according to Libet, 200 millisecond mark was the point at which you were given the opportunity to veto an action. So those are completely incompatible. So if Schulze-Kraft is right, then they have basically undone what Libet was saying about the veto.
Thank you.
Yeah, concerning that, what I didn't have a chance to get to in my paper is that there are some other experiments, and I can give you the references if you want them, that did seem to pretty conclusively show that the readiness potential, when they properly take into account runs of the experiment in which the person doesn't choose. In other words, they were told to get ready to make a choice, and then and I forget the details of the experiment, but basically what was correlated with simply being ready to make a choice of either a right or left button press, the readiness potential was always present, even when the decision of whether to press right or left had not been made yet. But what is correlated with the choice is the lateral readiness potential, which is the difference between the two parts of the brain correlated with that choice. And that was clearly active whenever they made the choice. And I'm not a neuroscientist, so I can't, claim to be expert on it, but there are good references that do indicate that the readiness potential is just that. You're getting ready to make a choice, but you haven't actually chosen yet.
I also just wanted to address something that I've noticed in the culture, I guess it's the culture of this question of free will, is that it seems to me that often I find neuroscientists, I was raised up in neuroscience, and I often find neuroscientists who believe that consciousness is produced by the brain and that there's no other sort of source for consciousness, are the ones who are also very firmly holding on to this idea of conscious free will, which is fascinating because they get pissed off when you find something in the brain, like Soon, or Lebet's original work before it was reinterpreted by you. They get pissed off and say, well, that's not an evidence of predeterminism. But where do they think, if they believe that the brain is making conscious experience, where do they think that's going to come from? There's no other place for it to come from. And so that's kind of a fascinating logical inconsistency that I see all the time.
Okay. We should move on to the last question. Last but not
Yeah,
least.
this is just a clarification for Aaron. You've added that nice flu model since I heard you give this at the ASSC, and I'm a little puzzled now about how to interpret it, because in the flu case, you have two factors. You have the kind of decline in your bodily function, plus you have the exposure to the virus. Neither one by itself will produce the flu. You need to have both. And I'm trying to think, is that what you're thinking here? Because I thought the way in the past, what's happening with this stochastic noise is when you cross threshold, that's making the decision. That's what pushing you into decision. And that, you don't need another, that's not like the another factor. That's not like being exposed to the flu virus now. So you've got this noise, it leads to push you over the threshold, that's the decision, and it's done. Whereas in the flu case, you really need to have two different things going on. You need to have the bodily decline, plus now but I don't think you want to interpret the conscious act as now like having the flu exposure as well.
Right, I can answer that very easily. So that's precisely where the analogy breaks down. The analogy just, for me, the analogy of the flu thing just serves the purpose of making a point. It's like an intuition pump in Dennett type terms. Okay. So that part, that's where the analogy breaks down. So you don't need an extra something.
Okay, good. So that's just a thing you might want to say, just so people,
yes.
You've confused me.
Okay.
Well, thanks very much.
Let's give Ron the last word there.
I just want to make one important thing that I learned from studying time. Much of what we talk about here in this room, and always on whether it's free will or the flow of time, is that there's too much debate over things that don't need to exist because we don't define our terms. And I would encourage those of you who haven't looked up some of the basic explanations for quantum mechanics. You have this complicated array of quantum mechanics, but there are relatively simple explanations to understand what delayed choice means and why some physicists say what you do now changes the past and thereby affects determinism. A simple review of those things can change your attitude about free will and time in general.
Thank you. All right, we really have no choice but to close right now. Let's reconvene at 11:20. We'll start a little late. with the next session, and we can go a little bit late since the afternoon is free. But let's give a big round of applause to what I thought was an excellent session. Thank you all.